Hi, welcome to this lecture on maps. My name is Dr. Ritesh Shajira. So what is a map? Well, a map models a searchable collection. So what do we mean by models? It has a configuration, a particular structure, which allows us to simulate a searchable collection of key value entries. Now this key value entry looks familiar. You've heard of them from the lecture on heaps. The key value pair, where key, it could be a numeric, it's a unique value that follows the partial ordering or total ordering. And a value can be anything. It can be an object from a class. It could be a cat, a dog, and from the animal class. It could be a ball from the snooker class, or whatever the case might be. A value here just means an object. The main operations of a map is for searching. We want to be able to go through the map and find things, insert things. We'd like to also delete things. So you can think of this as perhaps your friends on Facebook who your friend names on Facebook, right? You can search through them, you can insert new friends on your list of friends on Facebook, and you can delete friends on Facebook as well. So these are all the kind of operations you would expect to have. So we just have this notion of a searchable collection. We refer to that as a map. Now, multiple entries with the same key are not allowed. And this is in red. And the reason for this is quite obvious. If you have two keys which are the same, then to find those keys, you'll have an ambiguous search, right? You'll have two keys which are the same, and they might be storing different objects, but you won't have any secure way, because remember, this map it's hidden away. It's not presented to the user very explicitly. It's just this abstract notion of a searchable collection. So putting putting keys which are the same into the searchable collection, since we don't know how the structure is maintained, it could be very chaotic. So we restrict maps to have unique keys. And you can think of many examples of where we use maps. In address books, you have an address, and there's only one and only one address for each object. Maybe Margaret lives on 74 Honeydew Street, and Katie lives on 13 Ostrich Street. So perhaps if Katie and Margaret lived together in 13 Ostrich Street, you would just have perhaps the same address with the objects specifying both of these individuals. So you can think of many ways of doing that. But here's another example. At WITS, we have a system called SIMS. And this system stores all of the student entries, the student records. And we reference students by keys, because there's many Johns, there's many Ajudas, there's many Margarets or whatever. So what do? We associate the student with a student number. And the student number is exactly the key in this key value pair. And the object of the student is the value. So the object of the student will contain all of their personal information, their marks from first year, second year, third year, and so on. So this is stored in a map. So you can think of maps as a database in this way, using this kind of these applications. If you think of maps as a database, then you've got a way to search for these things in the database, search for objects, and you search for them by dereferencing a key. All right. So the kind of methods that you would associate with a particular with a map is, since we have this notion of a key value pair, let's just denote it as KV, where K is the key and V is the value or the object. The kind of methods we would have for a map is we can have a map it for key. So if you have a particular object, suppose the object from the class map. You can say that object name dot key, it'll return the key. The object dot value, it'll return the value. The object, you can remember multiple values. You could even have different fields. So the key, you have to have a key in the map class, but you could have many different characteristics. You could have values, you could have number, you can have address, you could have whatever the case might be. You could have value as an object in itself as well, like I've said before. You can also set the key, so you can change the key. But if you change the key, you have to make sure that whatever you're going to change it to doesn't appear in the map, because then if you don't do that, you might end up with duplicate keys. So if you're going to set the key to something else, you have to make sure that you're setting it to a key which will still be unique in the database, in the map. You can do the same for the value. So the most important methods here, sure, accessing the object is important, but this notion of a key, preserving the property of the map, the initial property of it having the multiple entries of the same key are not allowed. You have to maintain this property. If you keep that in mind when implementing a map. Right, so now that we have individual methods for the object inside of a map, we now can look at methods to search through this map. Remember, it's a searchable collection, so we want to be able to put things into it, take things out of it, search for things, change things, and so on. So in terms of the objects methods from this class, these are the methods for the object, but these are the methods for the data structure, for the abstract data type, which is this ADT. So for the map data structure, we have certain methods. We've got the find method, which finds the key K, and we can return an iterator to it. Remember, an iterator from the previous lessons, an iterator is nothing more than it references a position, and this position can be in the form of an integer to indicate the index of an array. It could be in the form of a pointer to dereference an address in memory from random access using things like linked lists. And when we want to find the K, we're searching for K, which is a key. Maybe it's a student number or an address. We want to return the object associated with that key. So we'll return this key value pair that we've got. We also want to be able to put things into the searchable collection. So we want to put things into it. So put KV, K is the key and V is the value. So we put the key value pair inside of it. Well, if we're putting a new key into this array, into this data structure, we must make sure that the key that has not been put in before, which means that we need to search the collection first and find out if K is already in there. And if it is, then we can't put it in. If it isn't, then we can insert it into it. Okay. Now, right now, I'm sure many of you are thinking of ways of implementing maps. Okay, so you must be thinking of, oh, I can implement this using an array of objects. I can implement this using a linked list. I can implement this using a hash table, or not a hash table. What is this? A heap. Well, you could, provided it's a searchable collection. You could use whatever you like, but you have to make sure that these functions are preserved. So I think the best way to think about this right now is not using more sophisticated structures like heaps, but rather think of using linked lists to implement a map. That's a doubly linked list, perhaps. Think of using arrays to implement a map. Okay, so that brings us to the third method, which is erase K. And if we are removing K, well, we have to search through the entire collection to find K. And in the worst case, given our luck, the K, if we're trying to remove, is at the last thing we'd be looking at, the last element in this map. And so to erase something from a map, it does take a lot of work, because you've got to search through it. Find it and then remove it. In the worst case, it's not even in the K isn't even in the map. And I invite you to think about the complexity of these things. Let's discuss it actually now. Just before we do this last method, size. Well, this just returns the size. How many key value pairs are there in the map, and whether or not there are any key value pairs in map. That's empty. Is empty. We also have methods of referencing the first thing in the map and the last thing in the map. Now, depending on the structure, this will differ. But if you think of it as a list, it'll be the first element. You'll be returning the first element, and end will be returning the last element. Okay, so then let's think about the complexity here. So what is the complexity of find K? Okay, so let's go to find K. Find K. Well, to find K, I've got to search the collection. If this map was implemented with an array or a linked list, well, finding K would require me to go to each and every cell or each and every node and search for K. So the complexity of find K is O(n). The complexity of put KV, well, if it's an array, I could just perhaps shift all the elements by one and put it in the first position, or I could just append it to the last position of the array, or the last vacant position of the list. In the case of a linked list, you can put in the, you can add to front or you can add to back. But the problem with this is we first need to find out if K exists in the data structure. Because if K does exist in the data structure, we cannot put it in, because then we'll have duplicate keys, and duplicate keys are not allowed. So what do? We spend our time searching through the collection, looking for K, and if we find K, we don't put it in. If we don't find K, then we simply insert it in the collection. We can add to the front or add to the back or add at the first vacant position of an array. It really depends on the implementation. But my point here is the complexity of put KV is ON, plus a constant, which we can ignore. The size, this would be O1, because we could make it an ON implementation if we wanted to, counting the elements every time we call the method size. Or we could be smart about it, and every time we put something in the map, or inside the map, then we just increment size. We increment a counter. And whenever we call the method size, we just return the counter. That's another way of doing it. For the method empty, all we need to do there is just check the value of the counter. If the counter is 0, then we can return true. It would be empty. And if it's not 0, then the counter would be 1. If size is not 0, then our empty will return true, which is a 1. The implementation for begin and end just dereferences the first and last element. If you implement this using a linked list, that's easy. You can just dereference tail and head. If you want to use an array, you would dereference the position of 0, because that will be the integer 0 would dereference the first item of the array, and the last item of the array. Obviously, you might not want to go to the end of the array, because you might have some empty cells. So you would need to dereference the last element of the map by looking at the value of the counter in size, and that will tell you where the last position is. And that will be what you return when you call end. Right, here's an example of a map. So looking at this example, this first command is checking if the map is empty, and we return true because the map is indeed empty. Then we put 5a. Okay, so you output 5a, and you put 5a into the map. So this is the map on this side. And you put 7b. All right, and your map will now have 5a and 7b. Then you put another thing in 2c, put another thing in 8d. And this is what the map now looks like. So we then put a third, what is this, a fourth thing in, and so this is our map at the end of it. Well, to find 7, remember, we need to search the entire collection. So we look at the first thing, it's not there. We look at the second, there it is. So we return that with a key value pair. Find 4, well, we look at, no. So there's nothing in here. We return n to indicate there's nothing in here. There's no key 4 in this map. And so on. You find 2, check the size. If you were keeping a counter, this counter would have been iterating when you were putting things into the list and erasing things. You would decrement the counter. So increment when you're using put, and decrement when you use erase. So put 5, your counter will be 1, then 2, then 3, then 4. And then when you check the size of it, it will return a 4, which will be the saved value in that counter. Erase 5, you'll have to search the collection. Successful erase would decrement the counter, so from 4 it will come to 3. Erase 2, find 2, and empty. Yeah, all right. So this is very straightforward. Something I like to draw your attention of is this. The put returns something here. Okay. Sometimes you'd be asked to do that. Sometimes, often not. Your put might have a return or might not have a return, but as long as it gets put into the map, that's what matters. So as I said before, you could implement a map using an array or using a linked list. So using a linked list, you could actually implement a map efficiently. But remember, efficiently here is a bit ambiguous because it depends on the application. Depending on what you're using the map for, efficiently will mean it'll vary. The definition will vary. Well, in a sense, the list is efficient because it doesn't have any empty cells. If you're using an array, you would have many. You remember, you have to declare the size of the array before you begin, and depending on the size of the map, it might use the array optimally or it might not. So something else to bear in mind is, in contrast to an array implementation, the linked list implementation doesn't require any swaps. Because in an array, if you are removing a node from the middle of the array, or you're removing a key value pair from the middle of the array, you would need to do swaps. All right, you'd have to do k swaps. It's k minus n, where k is the position of the element to be removed. So that's a lot of swaps. And that's something else to consider. So if you are removing things from the map, then you might have to think twice. If there are many removes, you might have to think twice about using an array to implement a map, because the number of swaps might just damage the computational complexity, increasing the computational burden, and that might be a problem. So really, the word efficiently here is up for debate, and I'm actually very happy for students to debate this, because you can think of applications where it will be efficient and applications where it won't. We'll talk about that a bit later on. So if we do use an array, we simply need a pointer, header, and trailer, and this will be the pointers that are pointing to the first item and the last item. It's drawn a bit differently here. Usually I draw it from the top, header pointing from the top and trailer pointing from the top, but it's the same concept. Here you have a pointer to a node, a pointer to an object, a pointer to an object, a pointer to an object. This is the node object, and these are your entries. So your node here, you can say class node, and then you can put in a key is equal to int, and then your int could be a phone number or a string for an address or whatever the case might be. But you'll have these node objects. Okay. Now, while I'm talking about this, I'd like you to think about which would be a better implementation. Okay, because you could implement this using a singly linked list or a doubly linked list. And while we're discussing this, think about how would the computational complexity increase or decrease depending on whether we used a singly linked list or a doubly linked list. This is important because it has a lot of computational consequences. So in terms of complexity, so it's something to think about while we're talking about this. All right, so there are some implementations of the various algorithms for maps. The first one here is the find algorithm. So I'm just going to go through them quickly because these are very straightforward. So finding k, all you would need to do is traverse the map. So S here is the map, S.begin and S.end, going from the first position to the last. We're going to check if the key is in that particular position. If it is, we return it. If it isn't in the map, and we will go through this for loop, and then at the end of it, return end. Because there'll be no entry with that key. You could also return null, or you can return end, or you can return no, sorry, there's no key in here, or whatever the case might be. Depending on what you'll be using this for, you would return various things. So all right, so then what is the complexity here? Like I said before, it's O(n), because in the worst case, you're looking for something that isn't there, or you're looking for something that's at the last position. And no matter how you implement it, if you're looking for something and it's the last place you're looking and you find it, or if you don't find it at all, then you would be in the worst case. On the other end, the put algorithm, right? We want to put a new key value pair into the map. Well, we're looking at this. So we're looking for the key first. That's how we have to start. So we say, well, for each P, we search the collection looking for K. All right. If we find the value, if we find our key, then we cannot insert it. Okay, we return. Because we return the key value pair that's already there with the same key. If it's not there, then we can just insert at the back or insert at the front of our linked list. After we do that, we now need to increment. Remember that constant, that variable counter, which counts the number of entries inside of it. And this is what we'll return when we call the size function. to find out the size of the map. So n is equal to n plus 1 because we've now successfully inserted something in. Okay, if we returned at this point, then these wouldn't have run, so we wouldn't be incrementing unnecessarily. So the computational complexity here again, even though it was so simple just to add to the front or add to the back, the burden sits here where we need to search for it. Same concept with erase, we have to look for it. So we now begin looking. So we start at the first position looking for the key K to erase it. If we do find it, we remove it. This might have not been a good idea to call the name of the algorithm and also the command to erase the node the same thing. So let's just ignore this and say remove. We'll just say remove it from the list, and then you can just, depending on where you find it, you would have to, in the case of a doubly linked list, if you are removing something from the middle of it, you do know how to do this. If you don't, have a look at the lecture slides on this. All you would need to do is rearrange the pointers, so you would so you could successfully remove the node from whichever position it appears in the linked list. And once you do that successfully, you need to decrement the size because you've taken something out. So there's one less thing in the map. So this last slide is just talking about the performance, but we've been speaking about the performance all along. So put takes on, all right, because we need to determine whether it's there already. Find and erase take on because those require us to look for something. In the worst case, we find it, we don't find it. In the worst case, we find it in the last position. And as it says here, we traverse the entire sequence to look for an item with the given key, and that's what takes a lot of the time. Yeah, so that's maps. When would we want to use maps? Well, maps, we use them everywhere, right? We use them, Facebook uses maps to store all of the different people who use it, friends and people who have accounts registered with Facebook. They have a large map to basically maintain that. But you can imagine having, I don't really know how many friends there are on Facebook, but there are a lot of people who use Facebook, quite a lot. And having a linked list implementation for Facebook, all right, this is a massive database of people. You can think of Amazon's books. How many books do they have? My goodness, a hell of a lot of books. And books with different titles and different authors, if not millions. I don't really know how many. I'll be like Carl Sagan and say there's billions and billions of these things. Actually, he never said that. I don't know how that actually got associated with him. But my point, I digress. My point is that in those cases, we have large searchable collections, very large collections. And using a linked list to implement a map might not be an efficient way of handling this kind of databases. So we need to think of cleverer ways of doing it. So look, we do use linked lists and arrays sometimes when we implement maps. We can. And it depends on the application. So look at this. They say here you could use this linked lists for just as a historical record of logins to a workstation. So just to say who's ever like you use the computers in the labs. You haven't been using the computers in the labs recently, but suppose the admin wanted to keep track of who uses the computers. He could just implement a small linked list based map, which allows us to store the details of the people who log in. Perhaps it's just the password or maybe the username or whatever the case might be, and that's a very small, it might be a very small list because per day perhaps there's only about 2 or 3 people who use the machine. We're not deleting things from here, we're not finding things, we're just storing the information in the rare case that we want to actually use it. So in that case it makes sense to use a list based representation because it's very cheap to implement one. It's not difficult to do it. It's quite easy. But for Facebook and for Amazon and for all of those big databases out there where we need to store this information, I don't know how many times I got kicked off Facebook or how many times I deleted my Amazon account. I don't know how many times I had to change my details on Google because of security reasons or whatever the case might be. But there are many times when people, you can imagine your friends going on and off Facebook all the time. They need to be able to handle this. And if you have a large collection of these people who use Facebook, let's call them Facebookers, then you need a way to easily put them on and take them off and change their details and stuff. And a list will not do for that, because in a case of 1 billion users, your computational complexity, it'll be O of 1 billion, which is just too large to go through individually. Even though it might seem like with today's computers it'll be fast, the problem is that you sometimes have to do many of these at the same time, which is just not efficient. So we need a smarter way of doing this. That's my point. I did speak a lot of 2 minutes talking about that. So we need a smarter way of doing this, and we're going to discuss a smarter way to do this in the next lecture. Thank you.